is a natural, that is easy. So that is when it's your turn to work on the problem, to solve the problem. Then you will have, may not have that proficiency, right? So you have to really have to practice. So today we will give a review of the second part. So the second part, we have four topics: structure, recursion, and induction. That gives us the recursive definition and also the structure inductive proof of certain properties. So the recursive definition is perhaps the most essential skill that you were you have to that is needed for your future studies. For all of this dynamic programming, or for a special case, divide and conquer and greedy, you essentially need to reduce the problem to a smaller problem. So that gives you a recursive definition. So if you have nice skill set, then the future problem will be I'll say it's a bit much easier. You will have easier time in the future. And then the other three parts more related to the counting. The combinatorial counting. We just we only need to learn a few basic things. The subsets or permutations or partial permutations, and we have those simple rules. And then from there, we can, for example, count all others using the Bar-Jasher rule or the suggestion rules or division rules. So that's again the Bar-Jasher here is a term reduction. And then we consider we learn probability. Probability, we have probability for all probabilities and random variables. You have to be clear about what is the sample space, what outcomes appear in the sample space, and what are their individual probabilities. And most importantly, you need to have a clear definition of the events. For the space problems, the events, just as it is described in natural language. For us to solve the problem, we have to provide the precise definition of the events. We have, in all of examples, we provide those steps. That is uniform probability space is simple. We just need to specify the probability space and events. And for the uniform probabilities, probability space, the problem actually kind of problem reduced to the countings, right? Counting the outcomes in the event, and count the outcomes in the intersections, or count the outcomes in the in the sample space. So the counting method, technique, skill is needed for calculating probabilities. You can see, you can observe that this is the practice set relies on that. So for expectations, the most important or most useful one is the linearity of expectation. That means we say when we count the number of events, we introduce the indicator random variables, and then the counting becomes the expectation of a random variable becomes the summation of the expectations. So that is perhaps the most useful, and also perhaps the easiest. So the problem practice set essentially covers all the basic ones. And as you can see that this is the problem easier than the homework problems, then this is the lecture examples or recitation examples. So we will go through these questions one by one, and I hope some of you can volunteer to explain your solution to others. And if you do that, I may give you partial credit at the end of this semester. If you do that, I may give you partial credit. Especially say if you're on the boundary, right? If it's like 88 or 87, I may give you like 3 partial credit to lift your grade. I say that's the award for you to your contribution to our community. And the solutions may not be unique. May not be unique. There may be some multiple solutions, especially for the counting. So there may be different ways. So if you like, you can share your ways to all of us. So let's start with the first problem. It's the counting the number of it's not counting, it's more like I say recursive definition or an induction of the number of triangulations of a convex particle. And in the feature class, when this actually is, you might learn a dynamic program, always for finding some optimal triangulation. So a triangulation may be associated with some kind of cost. You want to find some triangulation with minimum cost. And that's a standard problem. Classical is a textbook example problem for dynamic program. And if you know those type of recursive definitions, then those kind of dynamic programming will be in the future, right? Will be like a piece of cake. That only those problems only introduce the cost. So the recursive definition give us we can find the best one among all possible triangulations recursively. Alright, so this actually is the problem. Is one of the variables of the Catalan numbers. In the class, I already gave you 3 examples. One is the number of n-pair balanced princesses. The other one is the number of different multiplication orders on n plus 1 terms, right? Those are the ones covered in the lecture. And in the recitation, the TE also is went through another example. That example is even harder, tricky, not hard, tricky. More tricky. They say the ones in the lecture, and well, of course those are the much easier. I kept those easiest for exams. I said there are a lot of questions, right? A lot of the questions for like this, kind of numbers. I kept those for the exams. Those easiest for the exams. So this one is easier than the others. There is the staircase partition. There is the recitation example. How do you say slides? Is staircases, right? Into n rectangles. N staircase into n rectangles. Here, this is a similar question, similar nature. How many is it we want to get the recursive definition, actually, without the recursive relation. The number of triangulation. In the problem set, I gave the triangulation, possible triangulations of pentagons. Here I say, for this illustration, I gave all the triangulations for hexagons. And you ask to say, confirm or verify this secondary recurrence. So that means that this TA, right, is a catalytic number. So any of you say would like to share your approach? Any of you? Try to keep it. I promise I will give you credit. How to derive it? I mean, there is the derivation actually is similar for all of similar template, right? And our similar argument. How many of you say, well, it's fine if you don't want to share with. How many of you have know how to solve this problem? No? No one knows how to solve this problem? God bless you. Alright. Same as princesses, same as all of these three examples. Right? Here is the class. We fix one side, let's say between, we number them is from 0 to n minus 1. So we have this is because it has a plus 2 sides. Then we fix one side, let's say top side, horizontal side. And for any triangulation, this side must appear at the side of a triangle, right? Look at this, all possible triangulation above. So this side must appear at the side of triangle. Then we consider all possible triangles using this one, the top side, right, as a side. Are possible triangles. Well, we already have, you see, for a triangle, right? We already have one side, we only need to identify the other vertex, right? We only need to identify the other vertex. How many possible vertices here? Any of other remaining n vertices, right? Here, it is for n equal to 4. So those from 1 to through n. This n equal to 1, no, actually this first vertex, second vertex, third, and the last. Well, those are the possible triangles, or possible triangles. That corresponds to summation. This is the summation. The I corresponds to the vertices. So for each one, let's say for I here, then this is already a triangle. Then we need to say for the triangulation, we need to find the triangulation of this polygon, right? And let's say this is left. This is the left, this is the right. This triangulation of this polygon and this common polygon. This one has I minus 1 sides. So it has Ti minus 1. And this one has n minus I sides. So the normal triangulation for this part is Tn minus I. The same is the derivation we get. Simply, for all of the problems, look at the lectures, right? For this is the balance process, for this is the multiplication orders, and for the staircase partition. They all follow the same approach. Right? So that's how we get this recurrence. Is it clear? Any question? No question? What? Mike, what do you say here? Not this Mike, this Mike. Mike?
You fixed one side and you
yeah, and you pick all the possible choices, right? For each choice, then we get the left side and the right side, right?
And then the right
partition
side
is recursive, right?
I minus 1.
Yeah, and this is m minus I, right? Any question? It's fine to move on. Okay. The second one actually is the partitions, right? The partition, the recurrence, the number of K partitions, and we use the princesses. It's similar to the binomial. And we have this kind of recurrence. And this recurrence is similar to this Pascal triangle. By the way, this actually I brought this slide from the recitation. I think this is because of this program. This asks you to read it by yourself. Did you see later on say the orientation here is go over this slide. The Kanki. Did he go over this slide? Rotation, no? Because we skipped that, alright? If I ask him to say to cover the slide on the computation with long cycle, because that way is needed by a letter recitation problem or the 100 principal problem. Alright, so this is all of those. Actually, there is a class of problems which demonstrate the similar behavior as a Pascal triangle. Pascal is a recurrence. Pascal triangle, this remember is how is the binomial coefficient optimized, and we have this type of recurrence. This is like a two-dimensional recurrence. We have two parameters, n and k. For binomial coefficients, we have this recurrence. And for other similar counts, common counts, we have the similar property. Look at this number of suggestions. Suggestions in the class, we derived explicitly the expression. Here, in this rotation problem, we derived this recurrence relation, the recurrent. And this actually is from this recitation slide. I asked you to read myself. The solution actually, is similar. Okay, so it follows all of those templates. We count by cases, or classify. We have double counting, right? We classify sets into different types. So this actually is the word for counting number suggestion from a set of n elements to a set of k elements. And in this, for this is a slide actually for this problem, this contains we classify the suggestions. First, by the images of the last number, n. The image can be any number b, right? B in the codomain, among the k elements. Could be anyone. So that we have k choices for the image for n. That's why we have this blue factor k in the coefficient. Now for each fixed image b, we classify them into two types. The first type 1 is that the pre-image of b is the singlet. Only n is mapped to this image. The other one that is the pre-image b is not singlet. That means there are some other elements, the a, which are mapped to n, mapped to this b. And those types have counts, the first term and second term respectively. We will show that's our target. If we can show that gives us this recurrence. Alright. Well, the first part is if we delete A and B, right, this pair, because A is mapped to B, and only A mapped to B. So then if we remove this mapped pair, right, or this assignment. Then we get this suggestion from the first n minus 1 element to the k minus 1 elements, all elements other than b. And this actually is the projection. We can say the reverse that we can add to the back. Or it's if we would like the recursive definition. We define, we first they say generate all they say projection from n minus 1 to all those projection, and then we append them. This is for type 1. Type 2, similar. For we delete this n, then we still say get the projection from m up to this k, the entire k. Because what? This actually probably is the restatement slide. Because you see the image B, alright, has also is another is a pre-image. So this give so other detail was to get this suggestion. And the reverse is again by adding this pair back. So this is the way is, and for all the problems, for all derivations, we follow those kind of we follow those kind of template, right? Double counting and classifies it those that by some rules. And then we count. This is the size of each type. For the partition, actually we can't get this relation from the previous slide. Because the number of partition, k partition, is actually the number of suggestions divided by k factorial. However, it's a lot to go through this number k is to derive this recurrence directly. Where is it? You can look at this here, right? Again, so we have this triangle type of recurrence, possible, similar to the Pascal triangle. We classify the partitions, k partitions, into two types. The first type that n alone forms a part. The second type that is n and others together form a part. And we want to show that for the first part, for first type we have this number, for second type we have this number, right? And together is we get our recurrence. Think about, those are kind of the template for you to approve. Those are general enough, right? For other problems, we probably come template. So there is we come to the first type. What is well, if we delete this part, then we get this partition of first n minus 1 numbers with k minus 1 parts. So that's how the n minus 1, or k minus 1. And this can be reversed, right? The reverse is that we just have this new part, circular part. For type 2, we have to be careful about this n, this k, right? Let's say why so we have to have this k factor. Again, so we delete n from the part of containing n. And because n shared with our, so after deletion of n, then that set is still in the empty, right? So it's those is the remaining set, right? Formula is K partition, still K partition of n minus 1. But how to reverse? For reverse, it's actually here the not suggestion. Actually, it's K to 1 suggestion. It's actually it's the recursive definition that for the recursive definition, reverse the kernel recursive definition. For every say partition of K partition of n minus 1 of the first n minus 1 number, we choose this partition and one of its parts, and then insert n to that part. That gives us a K partition of n elements. This is like a recursive definition. Reverse part is like a recursive definition. So we have K parts, right? We have K parts, so we have K choices. And this is the number of K partitions of n minus 1 elements. That's how I get this second kind of second type. Right, so there are several other problems like this, like similar patterns, like they say Pascal triangle, right? The only difference about the coefficient. For the Pascal triangle, we have one it's just a y, right? Y and y. For the suggestion, we have k and k. For the partitions, we have y and k coefficient. So the general is kind of the same, right? Okay, so the purpose for the practice, right, is that you have to know how to derive them, right? How to classify into cases, into types, right? And typically for those type problems, I give the hint how to classify them. The practice set, I give the hint. Right? So to classify them in types, and then just get the account, or get the recursive for each type, or to get the recursive definition of each type. So those for all our problems, that is the double counting, combinatorial proofs, or derived recurrence, we have this similar pattern. So for the type of partition problem, again, I said you should really have practice solve by yourself. If you just read my simple solution, there is if you have a different problem, you won't be able to do that. You have to really get your feet wet. So all of this for same is techniques. Right, so this problem is clear, right? Any question? Don't be shy. You can ask questions anytime. So the next one I don't have slides, but because it's so simple, I can give this is the content directly. So the first question 3 is the counting functions. Question 3 is those are basic contents. So first, here we consider all the functions from n to n. The first one is how many functions? How many functions from? That is the first one, the most basic one, right? Give me the answer. This one I say is just from the slide, right? Patrick, how many functions from n to n? That's from the slide. Yeah, try. That's fine. If you made a mistake, that's fine. How many functions? Yeah. From a domain of n elements. Let's say it's n by to n goes. What? What?
Infinite number?
How can they be infinite? It's impossible to infinite. You can have infinite functions, infinite many functions. How many functions? That probably is the slide, right? Probably is it. From is I mean, those are the mostly the basic ones. Just using the counting rules, right? But it's part of the rules. That's actually what is the most basic one we start with. One. How many functions? How content now? Have we tried? I always say the count by names, but you have to use the other. Just random. Natalie, how many is a function from n to m? Yeah. How many functions from? Yeah. Wait, ask Natalie this time. What?
3.
How you get 3? You should should depend on N and M, right? Just wait, I ask Natalia this time. Now is I should be able to tell is which full apparatus or not. Alright, let me get another one.
Why is it coming to the end?
Mathilde. Mathilde.
Yes.
Oh yeah.
Yeah, what was the question?
The question is number of functions from N to M.
Oh, so like
Yep.
one, and then like it's all of them. And we have to do it off of ends. So there's an end to the end.
Yeah, three.
Natalia already said 3. I say you should something depend on say N and M, right?
Wait, how are they getting through it?
I don't know, to be honest.
What?
I don't know.
Okay. Did you practice?
No, I'm not talking this.
Right.
It's crazy.
Thank you for being honest.
Yeah.
Yeah. Oh my god. We're not gonna pass.
What?
Is it M?
Oh, sorry. Yeah.
Me?
Well, yeah.
Okay, is it M to the power of N?
Right. M to the power N or N to the power M.
Oh,
For each one, you have this N students, right? For each one, you have M choices, right? M choices. So it's M to the power N. Thank you. I say, remember the name is Mora, right?
Yes.
Okay. Thank you. Thank you very much. This is the first one, alright, in the slide. We'll start with the counting. How many functions? Second question. How many suggestions? How many of the suggestions? We already have this slide. I say it's in the class. If we use in the lecture, we have the slide on the principal inclusion and exclusion, right? We have the explicit expression. We have the explicit expression of suggestions.
And we can theoretically be the M in this case, since there's, the partitions are basically the slots we're able to fit them in, basically, so it would be, so, at least if I'm understanding, right?
The number of function suggestions. Here, well, if the suggestion is that it's necessary that N is greater than equal to M. That's not this is an assumption applied. That explicit expression we derived, right? In the principal inclusion and exclusion. As I mentioned, well, in the previous slide, I gave this recurrence, but in the lecture, we have this this explicit expression. See the number of injections. For a number of injections, it's necessary that N should be less than or equal to M. Right? Again, this is given in the first slide. Right? In the injection, in the application of the production. And this is the basis of the velocity power, right? Velocity power is the process would have no shear velocity, right? What's the probability? This is the permutation, partial permutations. Guys, if you do not practice this, for the final exam, at our skip this practice set. This is like courtesy, but you say, if you do not want practice that, it's just a waste of all of our effort. So the next two questions is D is the number of strictly increasing functions. Again, I always say curve by name. Curve flower. How many is it strictly increasing functions?
I don't know.
Did you practice?
I didn't have time.
Well, thank you, be honest. But can you try now? If what do you mean by is strict increasing functions? If you choose the image, right? If you choose any of these, the M images, right? Then there is a unique assignment, right? Because the function has strict increasing. So this is essentially that is you choose an element from M. Let's say here we have M boys, M girls, right? They will dance with each other. Right? And if you choose exactly say N out of M. So here this is simply say M choose M. So the problem 5, there is weakly increasing, not necessarily strictly increasing. Could be say some is a two element, maybe mapped to the same one. Again, it's our curve by name random. Okay, thank you.
I had a doubt. Shouldn't that be N choose N instead of M choose N?
Now here, this M is larger, right? If it's strictly increasing.
Okay.
M is larger. If the strictly increasing, M could be not small, right? That's a good question, is because we really have to be careful about which one is we choose which number from which number. Alright, so question E.
Well, I was thinking about, I think I had E is like basically it's going to be one. It'll be one less than, so at least be one less than J based on like actually.
It is close.
Yeah, because basically since the number since they're like connected, they're basically we know that I is less than J, so there's at least one. So there's going to be at least one less. Since all the integers in I are less than all the integers in I are less than J. For all integers I and J, with one with I, which is the minimum, being at least one, like equal to one, and then J has to be it has to be higher, but like in max being equal to n. So that means I guess.
Yeah, you have to find the ways to reduce the problem to the one we know how to solve. there are two ways. Right? Also similar way, the way has a clear closure theory that is if you have a mapping of m elements, right? You for m elements you choose. Let's see. You choose, let's say, images, right? Because it's increasing. And then you say for each of them, you choose any of them, here was 3, right? Could be, say, that could be the same. And then you say define, say, those separate the sequence of m, let's say, ones, right? Into mass of x1, x2, xn. And x1 plus x2 plus xn should be, let's say, equal to m. Well, x1 should be at least 1. And all others are non-negative. We only have xy is said to be at least 1. Here, this is less than equal to m. Well, it's less than equal to m, just use the variable is a change, right? Replace x1 by, let's say, y1, right? So, this x1 replaced by y, this is one solution, right? y1, which, y1 plus 1, right? And then, so we drop this one, m by minus 1, by 1. In other words, we choose y1 equal to x1 minus 1. This is the variable change. All others the same. So then we get this is the non-negative linear solution. But here with the inequality, it doesn't matter because we can add a select map to make them equality. So for those, solution will be n plus n minus 1. Choose n. This is the one solution. The other solution is that is you just get this a projection between these sequence functions and this is the binary sequence. Binary sequence which has m minus 1 zeros and n ones. So the total number of bits is m plus m minus 1. Get a projection, right? Between say the weakly increasing function and those bit sequence. M plus minus 1 bit sequence with exactly say n ones. There is a projection on that. Think about it. It's not hard. This actually is how is I get solution immediately. From this projection, I can immediately get this n choose m plus 1 and n, choose n. Right, so this problem 3.
At least I have part of the logic at least figured out for 3, I think. Try this.
Well, that did not. I have few slides. Because the slide actually is again taken from the presentation. Alright, so the programs, right, how to count those how many of the type of hands? The hand here is we consider this is 5 cards. how many is it hands with 5 cards? It's 52, right? Choose 5, right? We have totally say 52 cards. Those are slides from the presentation. I shared with you much earlier. And for a kind, that here is like 4 tools and 110. The other one must be different, right? Because for is a suit. We only have 4 is a kind is a suit, right? We only have 4 cards. So because of 5, the other must be different. How many of them? Is that why you say 1?
I think,
As,
there's a lot of possibilities basically because in theory every time, like for example, the first one, which is exactly 1 pair, what's wrong with
no, actually we call it 4 cards.
so the 4 of a kind is the odds are because the first card can be any basically it'll let's assume we're first card basically the one we're gonna match the 4 with. The probability is
No probability. We just here the first card. This is just count how many of them.
well, it's 4 of a kind, so 4 of the same suit or value basically. So 4 twos in this case.
How many, Cesar? Well, I'll give you a solution. Alright, that's fine. Let me just so you already have a solution. Because those are same slides I get from this from the rotation. Alright. We first choose the 4 cards, the suit, right? How many is the choice? We have to choose a rank. 13, right? 13 choose 1. And then for the rest card, the last card. How many choice?
There's 12 possible ones. It's every other.
12 possible rank, right?
And then you also have to account for, it could also be any potential suit as well for those ranks.
And
For that
4,
last rank.
4 is the possible suit, right? So we have 48 choices for last card. You have a question? Alright, 4 house means we have a triple, same, and a pair. How many of them? Here, this is how the solution, right? First, we need to choose this suite, a suit, right? This kind, suit. We have 13 choices of the rank. We choose a rank, 13 choice, not the suit, choose the rank. And among those 4 suits, we have 4 choose 3, right? Choices. For the pair, we have how many is the choice for rank? 12 choose 1, right? And how many is this suit? 4 choose 2. We simply apply the product rule. Nothing is difficult. Right? Just apply the product rules. Two pairs. We have 2 pairs and a third is different. I already said here, and also every suit. Here I say we first choose the ranks of those pairs. The 13 choose 2, right? 13 choose 2. The rank. And for each pair, we choose 2 suits. This 4 choose 2, right? And I have square, means we go on 2 pairs. And this last one, we have to choose its rank. It's among the 11 remaining ranks. Right? 11 and then we choose the suit, or choose one. And the last one is an example that is every suit should be covered. Well, because every suit cover is at least by the PG form exactly one is a suit, right? Appear twice, right? For example here, the hearts appear twice.
So at least one of them, yeah, so at least one's gonna have, one of the other suits and possibly, and it's gonna be one of the just remain, I guess. Oh wait, the power, I get it, it's because the power, that's power of three, like.
Here is this, we choose the pair ranks, right? So we choose 2. And we have choose the suit, 1 or 4, right? And for the remaining 3, we have 13 choices,
Okay, that's.
right? Again, be careful. How to say which sequence apply this is application rules, is a product rules. And for this another country is related to this problem. Here we need this problem asks for the conditional probability, right? You see the conditional probability is the given condition that is the hand has at least 1 pair. How many of them? How many hands will contain at least 1 pair? Well, we consider complement. How many of them has no pair? Have no pair, right? How many of them have no pair? And this is the one number without pairs.
One quick question, when we're considering like no pairs, does that mean like, do we?
The rank.
Does like
The rank are distinct.
Okay, yeah, and then for like what, does one for, like, would we also count, for example, 3 of a kind, like as mentioned over there? Because it's not a pair, it's.
Yeah, but it's a subset.
Okay, got it.
Yeah, so, but this is for the base, right? For the sample space, reduced sample space. How many is the pairs without pair? With at least 1 pair. So we count this is the complement without pair. It means all of them are distinct. Well, for all of them have distinct ranks, here is that we choose 5 ranks out of 13. And then we choose the suit, right? And for each card, we have 4 choices. $55. I did the target. Because for each one, you choose a suit, right? You already choose the ranks. Then you choose the suit. And then say the 1 pair, 1 person that is exact 1 pair, and 3 others are different. Again, apply the production rule. Again, apply the production rule sequentially. We choose the rank of the pair. Choose the rank of the pair. We have 13 choices, right? And then we choose the suit, 2 suits, 4 choose 2. And for the remaining ones, we have to choose 3 different ranks from 12, right? And for each one, we choose 1 of 4 suits. This best cutting, or this just application of this is the production rules. And 3 of kind, similar. similar. We choose the three ranks, the rank of and then the rest two, right? There is the ranks and series.
Yeah, I was just looking over the thing I had and it's just written differently, but it looks like I was trying to write.
Looking
Like when I calculate the probability of one pair.
one pair. Which one? The first one?
Yeah, I was just trying, I was trying to get it, I thought I potentially got it wrong, but I think it's just there, right, something to the exact same.
Yep, Patrick.
For the 4 choose 4 for 3 of a kind, should it be 4 choose 3 because it's
Which
first-
one?
For 3 of a kind, it's 13 choose 1 and 4 choose 4.
We choose a rank. 30 choose one.
Yeah.
We choose a rank of these three. 2, 3, 4. Right? Oh, this, okay, it's tougher.
Yeah, that was.
It's 4 choose 3.
Yeah.
It's 4 choose 3, right? This is tougher here. Thank you. Yeah. It's 4 choose 3. And the similar questions is for counting, right? It's on the power boards in the station. Again, the similar is the production rules. So I give some examples. It's examples. Basically, for all of them, you can count. From 4, from 5, the first problem, they said, what is, we have n persons, d birthdays. N person, d birthdays. The standard setting of the birth chart. And the first question is that they say, what is the expected number of persons with birthday different from others? All of them, we can use, they said, and those, you can use, they said, the easiest solution, right, is using the linearity of computation. For each person, right? For each person, xi is that this person has a unique birthday. And the expectation or the probability should be 1 minus 1 over d n minus 1. This is the probability. And then for any n minus 1 others, it's n minus 1, that is a different probability. And then you have n persons. This is just apply this is the linearity of expectation using the together with the
Didn't a couple like it wasn't the power level, it was something that had like a roll down, like a lottery that had a roll down feature.
For both questions, there are a lot of variant questions. I just take 4 over here. From B is that they say what is the number of persons sharing a birthday with a particular person. And again, use for this using this law of the linear representation. We have for individuals, probability is 1 over d, right? Sharing the birthday. And we have n persons, n minus 1 persons. So it's n minus 1 over d. For Problem C. What is number of persons with birthday after a particular person? That's after the first person. Well, we have considered those ones which have different birthdays. This is n minus 1 over, from here is this is the expected number of persons with different birthdays. And each one has half probability. I think each one is half. So that's the solution. The last one, the number of different birthdays. What is this? Is the expected number of different birthdays. Again, now here is we count for each birthday. Here is the count birthday. We can look at this for each day, right? This day, whether it has a unique is the birthday. It has a birthday. It is a birthday of someone, at least birthday of someone. Then we sum them up. Right, so then we have details for each day. They say the probability is 1 minus 1 over p. Just apply the linearity of excitation, right? Problem 6 is again the linearity of excitation. For each position, you have to count what is the probability of. It is the local. Local is the minimum. Local maximum. And then sum them up. The answer should be, I will not go through the steps, right? Because this is the easy problem. Question 6, I think the answer, I remember the answer is n plus 1 over 3. Using the linearity excitation, right? Count this is the probability that each probability. If you have any question, you can stay here. Otherwise, I'll just skip. Right? That's why it's also easy. It's just the first question. You have R red balls and G green balls, right? Or P black balls. And they say the probability to choose a black ball is B over R plus P. The second question just uses the condition of the probability on the event. That is the top one is blue or is red. Just condition on those two cases. Derive the two probabilities. All right, guys. If you do not practice, right, I will not give you anything like this. Originally, I have an extra credit card. I may still keep it. So the total questions, there were 5 regular questions and 1 extra credit card. Right?
Cancels out one of the problems.